So, meanwhile, while Minkowski was saying all these mathematical niceties, Einstein was worried about gravity. When we talked about classical mechanics, the first thing we did is say, okay, let's imagine a specific force of nature, gravity. It all worked out very nicely in the Principia Mathematica. Newton told us both the rules of classical mechanics and his inverse square law for gravity. So Einstein very naturally figured he had special relativity replacing classical mechanics. Now he needs to replace Newtonian gravity. It didn't work. You know, there's sort of an obvious set of guesses you go through as a theoretical physicist. None of them work. You need to come up with something a little more profound. So Einstein hit on something called the principle of equivalence. Remember, even Newton had figured out that gravity is a universal force. Drop two things, they will fall at the same rate, no matter what their mass is, but also no matter what they're made of, no matter what time of day it is, and so on. So Einstein puts this into thought experiment form. He was the best thought experimenter in history. And he says, what this means is, in some way, gravity isn't really a force at all. Because I can't tell if I'm in a gravitational field. You know, I can sit here and I can do experiments. I can drop things and they will fall, and I will say, aha, gravity made something fall. But he says, I would say exactly the same thing if the Earth had disappeared and this whole lecture hall was in a rocket ship, accelerating upward at 1g. That hasn't happened. Do not be alarmed. But Einstein says there's no experiment you can do as long as we're locked in the lecture hall that would tell the difference. Gravity and acceleration are indistinguishable from each other. Now, you and I, that's the principle of equivalence, and you and I would say, aren't we clever for having thought of that equivalence? And then we move on with our lives. But Einstein was Einstein, and he's like, this means something. I got to be able to use this to come up with the right way to marry relativity and gravity. And he suspected that what he needed was more math. And he wasn't very good at math, like I said. I mean, he was good at it when he needed to be. He didn't do it for his spare time, though. Happily, one of his friends from graduate school, Marcel Grossmann, was an expert in what at that time was the fanciest mathematics and geometry out there. Here's Grossmann on the left. And so Einstein says, Marcel, you got to help me with this. And Marcel Grossmann taught Einstein what at that time was the most modern ideas in geometry. So what does that mean? What counts as a modern idea in geometry? Well, Euclidean geometry, which we talked about with Pythagoras' theorem, is based, as you might know, on a set of axioms, and the famously weird axiom is the parallel postulate. The idea that if you start with a little line segment, take two perpendicular rays and let them move off to infinity, Euclid says they will stay exactly parallel at the same distance forever. For many years, for literally centuries, millennia, I suppose, people tried to prove this feature of geometry based on Euclid's other axioms. When I was in high school, our geometry teacher gave this to us as an extra credit assignment to prove the parallel postulate. He was very cruel because you cannot prove the parallel postulate, as they realized in the 1830s, because you can replace it with other perfectly good postulates. You can say either that those initially parallel lines converge at a constant rate, or maybe they diverge at a constant rate, and you get perfectly good theories of geometry, different than Euclidean geometry, but perfectly good in their own right. If the lines start to converge at a constant rate, you get spherical or positively curved geometry. If they diverge at a constant rate, you get a saddle or hyperbolic or negatively curved geometry. And these were investigated, and they were just as good as Euclidean geometry. So people started to say, well, why does Euclidean geometry work so well in the world? What's going on? Other people said, we're still making an assumption here. The assumption we're making is that if those lines start to converge or to diverge, they do so at a constant rate. It was Gauss, Carl Friedrich Gauss, one of the greatest mathematicians in history, who said, look, once you tell me that I can have a sphere or a saddle or a potato chip, I can have any wild thing that I want. I could even have a 3-dimensional space, or a 4-dimensional, or a 29-dimensional space. And they could be diverging some places, these lines, and converging other places, like there's suddenly an infinite number of geometries that I could think about. Happily for Gauss, he had a very talented graduate student, Bernhard Riemann. And Riemann was already a well-known mathematician, but in the German system, like, there's a never-ending series of exams you have to pass before you can become a professor. And so the last one, the habilitation exam, Riemann gave Gauss a list of possible topics that he could study, and Gauss pointed to the one that Riemann thought was the most boring, the foundations of geometry. Do that one. And Riemann goes off, and it's hilarious to read this. I did this, for writing the book. For the first time, I actually looked at Riemann's paper, and he can't stop kvetching within the paper. He's like, I don't like doing this, but, I'm told to do this. It's not my natural métier. Riemann's purpose was to figure out how to, in absolute perfect generality, capture the geometric structures of a space in any number of dimensions without embedding it in any other space, just its own intrinsic character. So that's obviously, there's a lot of ways that space could curve or twist or bend or whatever. What is the simplest way to distill that down to some usable information? And Riemann, because he was quite clever, he figured out that if you know the length of every curve that you can draw, so imagine on this tabletop you just draw every single curve, both straight lines and curved lines and everything. If you had the information in your brain about the length of every curve, that would completely fix the geometry of the space. The only way that those curves can fit together is if the space is flat. Or in this picture, these are spheres with little balls of yarn, little lines crossing on them. Riemann's insight is that all you need to know is the length of every possible curve that fixes the geometry of the space. And how does it work? It's kind of like Pythagoras' theorem again, but because things are arbitrarily twisty, you zoom in. For those of you who know calculus, this is the traditional calculus trick. When things are curvy and changing, you zoom in, and if you zoom in carefully enough, everything looks straight and flat and constant. So Riemann says, I can take some arbitrary twisty curve, I can zoom in on it, and I can use Pythagoras' theorem. So in this case, this little 3-dimensional diagram, the length of a tiny little line segment is x squared plus y squared plus z squared, the square root of that. So Riemann's self-appointed task is, let's generalize this. The nice thing about this picture we drew is that it's actually in flat space. So I've drawn coordinates x, y, z. If the space is not flat, if I'm on a sphere or a torus or something crazy, I might not be able to use such convenient coordinates as x, y, and z. And in fact, what happens is when your coordinates begin to get a little bendy and curved themselves, the formulas begin to look a little bit more elaborate and less intuitive. So this may or may not mean anything to you. This is just for those of you who are familiar with the idea of spherical coordinates. So you have x, y, z, but you could also just say, what is the distance to the point? What is the angle from some line of longitude? Or what is the angle from the North Pole? That gives you spherical coordinates, which are very useful when you have spherical symmetry. And here is the formula for the distance of a little infinitesimal line in terms of r, the distance, theta and phi, those two angles. No information about that particular equation needs to penetrate into your brain other than the equation becomes more complicated when the situation becomes more complicated. So what Riemann needs is, what is the maximal complication? What is the most arbitrary way that we can think about this? You stare at this expression, you ask what is going on, and if you're Riemann anyway, you say, okay, I think what's going on is that I have on the left-hand side some interval. I would like to say some distance, but in space-time, it's going to be some time. So we use the word interval to mean either space or time. Some interval squared is on the left-hand side. That's what we inherit from Pythagoras. On the right, we have a sum of terms with all the different coordinates times some number, some quantity, right? So dr squared all by itself. But then the theta squared term has an r squared outside, the phi squared has r squared. Like, there's a whole bunch of things going on. The general pattern is some number times a coordinate times the other coordinate. So coordinate squared times some number. In other words, in space-time, for example, where you have t, x, y, and z, you're going to have a formula for the interval in space-time, just like Minkowski gave us, but maybe more general. So the interval squared is going to have some number times t squared, plus some number times t times x, plus some number times t times y. If you have 4 dimensions, t, x, y, z, there's going to be 16 terms. 4 times 4 is 16, right? T, tx, ty, tz. You can go through them all at home, or right now, in your head, if you're that good. It quickly becomes unwieldy, right? Too many terms you have to write out, it becomes boring. If there's one thing that mathematicians are very, very good at, it is inventing notation that makes unwieldy but understandable things into very elegant but impenetrable things. So they do that. They invent something called the metric tensor. And the first step here is to relabel your coordinates. You thought you were happy with t, x, y, z, coordinates on space-time, but someone reminds you, you might want to use spherical coordinates or something more complicated. So rather than t, x, y, z, let's call them x0, x1, x2, x3. Immediately someone says, why did you start numbering with 0? Well, it's because physicists, bless their hearts, like to imagine more or fewer numbers of spatial dimensions, right? Maybe only 2 spatial dimensions, maybe 9 spatial dimensions if you're a string theorist, but we only always have 1 time dimension. So give time the label x0, and all the spatial dimensions are x1, x2, x3, etc. And then the whole shebang, you call it x mu. So mu, the Greek letter mu, is an index. It runs 0, 1, 2, 3. Or if you want, t, x, y, z. Completely equivalent. x0 is time, x1 is x, and so forth. That's where the mu is coming from. Remember the mu? The mu's in the news from Einstein's equation, right on the second slide there? Here's where they come in. They are labels on directions you can move in space-time. T, x, y, z. So it's not really that new and crazy. And then rather than saying some number times t squared plus some number times tx, invent a new notation, g mu nu, and g mu nu is simply the number that gets multiplied by x mu x nu in that equation. So the interval squared in perfect generality is g00 times x0 squared, g01 times x0 x1, and so on. We have not yet achieved perfect inscrutability or compactness, so this is just the sum over all those values the indices take of g mu nu times x nu times x nu. That big sigma is another Greek letter. It means you sum over all the different possibilities. So these two expressions are exactly the same thing. This little purple thing, sum over mu and nu, g mu x nu, is just g00 x0 squared plus g0, etc. Okay? Now onto the stage comes Albert Einstein, who, as you might imagine, was doing his homework for Marcel Grossman, trying to teach him geometry, and he goes, this is very tiring, writing all these summation signs. I'm going to invent a new notation in which you write the same thing, but you don't write the summation sign. He was so proud of himself. He literally was telling jokes. He said, I've made a great discovery in mathematics. You don't need to write the summation sign. As long as you have repeated indices, you imagine that we mean you should be summing over them. This is called the Einstein summation convention. Not the most important thing Einstein ever did, but he got a kick out of it.